Imagine a world where robots can navigate any terrain with ease. Picture them traversing rocky landscapes, climbing stairs, and even venturing into disaster zones. This is the promise of Hexapod Robots, six-legged machines inspired by the agility and stability of insects. These robots are not just a figment of science fiction, they are a rapidly developing reality, with the potential to revolutionize various fields. From search and rescue missions to exploration of other planets, Hexapod robots offer a unique combination of mobility and versatility. Their 6 legs provide exceptional stability, allowing them to navigate uneven surfaces that would challenge wheeled or even 4-legged robots. This inherent stability, coupled with their adaptability, makes them ideal for a wide range of applications. But what makes these 6-legged machines so special? What are the fundamental principles that govern their movement and control? In the following sections, we will delve into the fascinating world of Hexapod robots, exploring their mechanics, capabilities, and the exciting future that lies ahead. Join us as we journey from the theoretical foundations of robotics to the real-world applications of these remarkable machines. Before we dive into the specifics of Hexapod robots, let's take a step back and understand the basic principles of robotics. At their core, robots are machines designed to perform tasks autonomously or semi-autonomously. They achieve this through a combination of sensors, actuators, and control systems. Sensors act as the robot's eyes and ears, collecting information about the environment. These sensors can range from simple touch sensors to complex cameras and laser scanners, each providing crucial data for the robot to perceive its surroundings. This sensory information is then processed by the robot's control system, often referred to as its brain. The control system, typically a computer program or a network of microcontrollers, interprets the sensory data and makes decisions based on pre-programmed instructions or algorithms. These decisions are then translated into actions by the robot's actuators. Actuators are the muscles of the robot, responsible for carrying out the commands from the control system. In essence, robotics is about creating machines that can sense, think, and act. Hexapod robots, with their unique locomotion and capabilities, represent an exciting frontier in this field. Understanding these fundamental building blocks of robotics will provide a solid foundation for comprehending the complexities and potential of Hexapod technology. Now let's zoom in on the stars of our show Hexapod robots. As the name suggests, these robots are characterized by their 6 legs, a design inspired by the remarkable stability and adaptability of insects. This 6-legged configuration provides them with a unique advantage in navigating complex terrains. Each leg of a Hexapod robot is essentially a small robotic arm, often with 3 degrees of freedom, allowing for a wide range of motion. These legs are connected to a central body that houses the robot's control system, power source, and any additional sensors or payloads. The body serves as the central hub, coordinating the movements of all 6 legs to achieve locomotion. Motors, typically servo motors, are used to power the joints of each leg, enabling precise control over their movement and positioning. These motors work in concert, orchestrated by the robot's control system, to generate walking patterns and navigate obstacles. The choice of sensors on a Hexapod robot depends largely on its intended application. For basic navigation, simple contact sensors or infrared sensors might suffice. However, for more complex tasks like mapping or object recognition, advanced sensors like cameras, LiDAR, or ultrasonic sensors might be employed. Why go through the complexity of designing a robot with 6 legs, when there are simpler alternatives like wheeled or 4-legged robots? The answer lies in the unique advantages that hexapods offer, particularly in terms of stability and maneuverability. The 6-legged configuration provides inherent stability, allowing hexapod robots to maintain their balance even on uneven surfaces. This is because they can always maintain 3 points of contact with the ground, forming a stable tripod while the other 3 legs move. This tripod gait ensures that the robot remains stable even when navigating challenging terrain. Compared to wheeled robots, hexapods are far more adept at handling obstacles. They can step over small objects, climb stairs, and traverse rough terrain that would be impassable for their wheeled counterparts. While quadruped robots share some of these advantages, hexapods offer greater stability, especially when carrying payloads or operating in unpredictable environments. This combination of stability and maneuverability makes hexapod robots ideal for a wide range of applications, from exploration and search and rescue to inspection and maintenance tasks in challenging environments. They represent a significant leap forward in robotic locomotion, offering capabilities that surpass those of more traditional robot designs. Section 5: Path Planning, Navigating Complex Terrains. Imagine a hexapod robot tasked with navigating a disaster zone filled with debris, uneven ground, and unpredictable obstacles. How does it determine the safest and most efficient path to reach its destination? This is where the crucial concept of path planning comes into play. Path planning, in essence, is the process of finding a sequence of movements that will allow the robot to navigate from its starting point to a desired goal point, while avoiding obstacles and minimizing risks. This is a complex computational problem, especially for robots operating in dynamic and unstructured environments. Several algorithms and techniques have been developed to tackle this challenge. These algorithms take into account the robot's capabilities, the characteristics of the environment, and the desired goal to generate an optimal or near-optimal path. Some commonly used path planning algorithms include Dijkstra's algorithm, a star search, and rapidly exploring random trees, or RRT. These algorithms differ in their complexity and computational requirements, with some being more suitable for specific types of environments or tasks. Section 6. Algorithms and action guiding hexapod movements. Let's illustrate the concept of path planning with a practical example. Imagine a hexapod robot tasked with retrieving an object located on the other side of a cluttered room. The room is filled with obstacles of varying sizes and shapes, requiring the robot to carefully plan its path. The robot's sensors, perhaps a combination of cameras and distance sensors, first scan the environment, creating a map of the surroundings. This map identifies the robot's current location, the target object's position, and the obstacles present in the room. This map data is then fed into the robot's path planning algorithm, which could be Dijkstra's algorithm, a asterisk search, or any other suitable algorithm. The algorithm analyzes the map, considering the robot's size and movement constraints, and calculates a safe and efficient path to reach the target object. The calculated path is then translated into a sequence of leg movements, with the robot's control system coordinating the precise timing and coordination of each leg's actuators. The robot then executes these movements, carefully navigating the obstacles and adjusting its path as needed based on real-time sensor feedback. Section 7. Hexapods in the real world, current applications. Hexapod robots are no longer just a theoretical concept confined to research labs. They are increasingly finding their way into real-world applications, demonstrating their potential to revolutionize various industries. One prominent application is in search and rescue missions. Their ability to navigate rubble, stairs, and other challenging terrains makes them invaluable tools for locating and assisting survivors in disaster-stricken areas. They can be equipped with cameras, sensors, and even communication devices to aid in search and rescue efforts. Another area where hexapods excel is exploration, particularly in environments that are hazardous or inaccessible to humans. Researchers are developing hexapod robots for exploring other planets, navigating the depths of the ocean, and inspecting hazardous environments like nuclear power plants. Beyond these extreme environments, hexapods are also finding applications in more everyday settings. They are being used for inspection and maintenance tasks in industries like construction, agriculture, and even healthcare. Their ability to navigate complex environments and carry payloads makes them ideal for these tasks. Section 8. Challenges and limitations, overcoming obstacles. While hexapod robots offer significant advantages, they are not without their challenges and limitations. One of the primary challenges is the complexity of their design and control systems. Developing robust and reliable control algorithms for 6 legs, each with multiple degrees of freedom, is a complex task. Another challenge is power consumption. The multiple motors required to power a hexapod robot can be energy-intensive, limiting their operational time, especially when operating on battery power. Researchers are constantly working on developing more efficient motors and power management systems to address this limitation. Furthermore, the cost of building and deploying hexapod robots can be prohibitive for some applications. The advanced sensors, actuators, and control systems required come at a price, making them less accessible compared to simpler robot designs. Despite these challenges, the field of hexapod robotics is rapidly evolving. Researchers are constantly developing new materials, algorithms, and control systems to improve their capabilities, efficiency, and affordability. Section 9. The future of hexapods, advancements and possibilities. The future of hexapod robotics is brimming with possibilities. As technology continues to advance, we can expect to see even more capable and versatile hexapod robots emerging from research labs and into the real world. One promising area of development is in the field of soft robotics. Researchers are exploring the use of soft, flexible materials to create hexapod robots that are more adaptable, resilient, and safer for interaction with humans. Imagine a hexapod robot that can squeeze through tight spaces, handle delicate objects, and even interact with humans in a more natural and intuitive way. Another exciting development is the integration of artificial intelligence and machine learning into hexapod control systems. This will enable robots to learn from their experiences, adapt to changing environments, and perform tasks with increasing autonomy. Imagine a hexapod robot that can learn to navigate a complex environment on its own, identify and classify objects, and even make decisions based on its surroundings. As these technologies mature, we can expect to see hexapod robots playing an even more prominent role in our lives. They will continue to push the boundaries of what's possible in robotics, opening up new frontiers in exploration, disaster response, healthcare, and beyond. The future of hexapod robots is bright, and the possibilities are limited only by our imagination.